Hello viewers of AraaTech, let's start our new topic, symbolic artificial intelligence. Symbolic artificial intelligence, also known as good old-fashioned artificial intelligence, GOFAI, or classical artificial intelligence, refers to the early approaches in artificial intelligence that were prevalent from the 1950s to the 1980s. This era of artificial intelligence was characterized by the belief that intelligence could be achieved through symbolic manipulation of abstract symbols and logical reasoning, mimicking the way humans think and solve problems. Key characteristics and components of symbolic artificial intelligence include logic and symbol manipulation. That's a key aspect of symbolic artificial intelligence. Let's delve deeper into how symbolic artificial intelligence systems represent knowledge using symbols and how logical rules are applied for problem solving and decision making. Knowledge representation. In symbolic artificial intelligence, knowledge is represented using symbols, which are abstract entities that stand for objects, concepts, or ideas in the world. These symbols can represent anything from simple entities like numbers or words to complex concepts like objects, relationships, or rules. Symbol manipulation. Once knowledge is represented symbolically, symbolic artificial intelligence systems manipulate these symbols using logical rules and operations. This manipulation involves performing various cognitive tasks such as deduction, induction, abduction, and inference. Logical rules. Logical rules encode the relationships, constraints, and patterns in the knowledge domain. These rules define how symbols can be combined and manipulated to derive new information or make decisions. For example, in a medical expert system, logical rules might specify conditions for diagnosing a disease based on symptoms reported by a patient. Problem solving. Symbolic artificial intelligence systems use logical rules to solve problems by applying reasoning processes to the symbolic representations of the problem domain. This involves breaking down complex problems into simpler components, applying logical rules to these components, and synthesizing the results to derive solutions. Decision making. In decision making, symbolic artificial intelligence systems use logical rules to evaluate different options or courses of action based on the available information and predefined decision criteria. Logical inference is used to assess the consequences of each option and determine the best course of action. Example: expert systems. Expert systems are a prime example of symbolic artificial intelligence applications. In an expert system for medical diagnosis, symbolic representations of medical knowledge such as symptoms, diseases, and treatment protocols are encoded using symbols. Logical rules govern how these symbols are manipulated to infer possible diagnoses based on observed symptoms and medical history. By representing knowledge symbolically and manipulating symbols through logical rules, symbolic artificial intelligence systems attempt to mimic human thought processes and reasoning abilities. While symbolic artificial intelligence has its limitations, particularly in handling uncertainty and real-world complexity, it remains a valuable approach in certain domains where explicit knowledge, representation, and logical reasoning are crucial. Expert systems. Expert systems were one of the primary applications of symbolic artificial intelligence. These systems encoded human expertise and domain knowledge in the form of rules and logic. They were used to solve specific problems or make decisions in specialized domains such as medical diagnosis, financial analysis, or troubleshooting technical issues. ChatGPT. Exactly. Expert systems were a cornerstone application of symbolic artificial intelligence. Here is a more detailed explanation of expert systems. Human expertise encoded. Expert systems aim to capture and replicate the problem solving and decision making abilities of human experts in a particular domain. This expertise is encoded in the form of rules, logic, and knowledge representations within the expert system's software. Knowledge base. Expert systems consist of a knowledge base that contains domain-specific information, rules, and heuristics. This knowledge base is created by acquiring knowledge from human experts through interviews, documentation, and other means. Inference engine. The knowledge base is coupled with an inference engine which is responsible for processing the knowledge and applying logical rules to draw conclusions or make decisions based on the input data provided to the system. Rule-based reasoning. Expert systems use rule-based reasoning to emulate the decision-making process of human experts. These rules are typically in the form of if-then statements, where specific conditions, the if part, trigger certain actions or conclusions, the then part. Example, medical diagnosis. In a medical expert system, the knowledge base would contain information about symptoms, diseases, treatments, and medical guidelines. The inference engine would use this knowledge to ask questions about the patient's symptoms, apply logical rules to infer possible diagnosis, and recommend appropriate treatments or further diagnostic tests. Applications. Expert systems have been applied in various domains, including medicine, finance, engineering, troubleshooting, and management. They have been used for tasks such as medical diagnosis, financial analysis, equipment maintenance, customer support, and decision support. Advantages. Expert systems can capture and codify the expertise of human experts, providing consistent and reliable decision-making capabilities. They can also assist less experienced professionals by providing guidance and recommendations based on established best practices and domain knowledge. Limitations. Expert systems are limited by the knowledge and expertise encoded within them. They struggle with uncertainty, ambiguity, and situations outside their predefined knowledge domain. Additionally, maintaining and updating the knowledge base can be labor intensive and costly. Overall, expert systems represent a powerful application of symbolic artificial intelligence, enabling automated decision making and problem solving in specialized domains by leveraging human expertise and knowledge. Rule-based systems. Rule-based systems are indeed another important form of symbolic artificial intelligence. Closely related to expert systems, predefined rules and conditions. Rule-based systems operate on a set of predefined rules and conditions, often represented in the form of if-then statements. These rules encode domain-specific knowledge, logical relationships, and decision-making criteria. Rule evaluation. When presented with input data or a specific situation, the rule-based system evaluates the applicable rules based on the input and the system's current state. It matches the conditions specified in each rule against the input data to determine which rules are triggered or activated. Inference and decision making. Once the relevant rules are identified, the rule-based system uses them to make inferences or decisions regarding the given input data. This process involves applying the logical operations specified in the rules to draw conclusions, derive new information, or take specific actions. Hierarchical structure. Rule-based systems often have a hierarchical structure with rules organized into different levels or layers based on their specificity and priority. This hierarchical organization helps ensure efficient rule evaluation and decision making. Example: business rules engines. Rule-based systems find applications in various domains including business process automation, decision support systems, and expert systems. For example, a business rules engine might be used to automate decision-making processes in areas such as loan approvals, insurance underwriting, or fraud detection. Each rule in the system specifies conditions under which a particular decision or action should be taken based on the input data. Flexibility and maintainability. One of the advantages of rule-based systems is their flexibility and maintainability. Rules can be easily modified, added, or removed to adapt to changing requirements or to incorporate new knowledge. This makes rule-based system well suited for dynamic environments and evolving domains. Limitations. Rule-based systems are limited by the comprehensiveness and accuracy of the rule set. They may struggle with handling uncertainty, complexity, and situations that fall outside the scope of their predefined rules. Additionally, managing a large number of rules can become challenging and may lead to rule conflicts or redundancies. In summary, rule-based systems are a key component of symbolic artificial intelligence, providing a structured and rule-driven approach to problem-solving, decision-making, and automated reasoning in various domains. They offer a flexible and maintainable framework for encoding domain knowledge and logic, enabling efficient automation of complex tasks and processes. Knowledge representation. Rule-based systems are indeed another important form of symbolic artificial intelligence closely related to expert systems. Let's delve deeper into their characteristics and how they operate. Predefined rules and conditions. Rule-based systems operate on a set of predefined rules and conditions, often represented in the form of if-then statements. These rules encode domain-specific knowledge, logical relationships, and decision-making criteria. Rule evaluation. When presented with input data or a specific situation, the rule-based system evaluates the applicable rules based on the input and the system's current state. It matches the conditions specified in each rule against the input data to determine which rules are triggered or activated. Inference and decision making. Once the relevant rules are identified, the rule-based system uses them to make inferences or decisions regarding the given input data. This process involves applying the logical operations specified in the rules to draw conclusions, derive new information, or take specific actions. Hierarchical structure. Rule-based systems often have a hierarchical structure with rules organized into different levels or layers based on their specificity and priority. This hierarchical organization helps ensure efficient rule evaluation and decision making. Example: business rules engines. Rule-based systems find applications in various domains including business process, automation, decision support systems, and expert systems. For example, a business rules engine might be used to automate decision-making processes in areas such as loan approvals, insurance underwriting, or fraud detection. Each rule in the system specifies conditions under which a particular decision or action should be taken based on the input data. Flexibility and maintainability. One of the advantages of rule-based system is their flexibility and maintainability. Rules can be easily modified, added, or removed to adapt to changing requirements or to incorporate new knowledge. This makes rule-based system well suited for dynamic environments and evolving domains. Limitations. Rule-based systems are limited by the comprehensiveness and accuracy of the rule set. They may struggle with handling uncertainty, complexity, and situations that fall outside the scope of their predefined rules. Additionally, managing a large number of rules can become challenging and may lead to rule conflicts or redundancies. In summary, rule-based systems are a key component of symbolic artificial intelligence, providing a structured and rule-driven approach to problem-solving, decision-making, and automated reasoning in various domains. They offer a flexible and maintainable framework for encoding domain knowledge and logic, enabling efficient automation of complex tasks and processes. Inference engines. Inference engines play a crucial role in symbolic artificial intelligence systems by facilitating logical reasoning and deduction. Logical reasoning. Inference engines are software components designed to perform logical reasoning based on the rules and knowledge encoded within a symbolic artificial intelligence system. They apply various logical operations and inference techniques to draw conclusions from the available knowledge and input data. Rule evaluation. One of the primary functions of an inference engine is to evaluate the rules within the system's knowledge base when presented with input data or specific query. The inference engine matches the input against the conditions specified in the rules to determine which rules are applicable or relevant. Inference process. Once the relevant rules are identified, the inference engine uses them to drive new information, make inferences, or reach conclusions. This process involves applying logical operations such as education, induction, abduction, and logical inference rules, that is, modus ponens, modus tollens, to manipulate the symbolic representations of knowledge and draw logical conclusions. Backward and forward chaining. Inference engines often employ chaining mechanisms such as backward chaining and forward chaining to perform reasoning and reach conclusions. In backward chaining, the engine starts with the goal or desired outcome and works backward through the rules to find the necessary conditions or evidence to satisfy the goal. In forward chaining, the engine starts with the available data and applies rules iteratively to derive new information until no further inferences can be made. Uncertainty handling. Some inference engines are equipped with mechanisms to handle uncertainty and probabilistic reasoning. They can assign probabilities to different hypotheses or outcomes based on the available evidence and use probabilistic inference algorithms to update beliefs and make decisions under uncertainty. Efficiency and optimization. Inference engines may incorporate optimization techniques and algorithms to improve efficiency and performance, especially in systems with large knowledge bases or complex reasoning tasks. Techniques such as rule pruning, caching, and parallelization can help reduce computational overhead and improve inference speed. Example, medical diagnosis. In a medical expert system, the inference engine evaluates the rules governing medical diagnosis based on the patient's systems and medical history. It applies logical inference rules to combine the available evidence and draw conclusions about possible diseases or conditions afflicting the patient. In summary, inference engines serve as the reasoning backbone of symbolic artificial intelligence systems, enabling them to perform logical deduction, inference, and decision making based on the encoded knowledge and rules. They play a vital role in automating reasoning tasks and simulating human-like intelligence in problem-solving domains. Limitations. Symbolic artificial intelligence, despite its successes, encountered notable challenges and limitations, particularly in dealing with uncertainty, ambiguity, and real-world complexity. Uncertainty handling. Symbolic artificial intelligence systems struggle with handling uncertainty inherent in real-world data and environments. Uncertainty arises from various sources such as incomplete information, noisy data, or probabilistic events, which are difficult to represent and reason about using explicit rules and logical operations. Ambiguity. Real-world problems often involve ambiguous or vague information that can be interpreted in multiple ways. Symbolic artificial intelligence systems find it challenging to deal with ambiguity effectively as they rely on precise representations and deterministic reasoning. Resolving ambiguity requires context awareness, common sense reasoning, and semantic understanding, which are difficult to achieve using symbolic approaches alone. Complexity. Many real-world problems are inherently complex, involving numerous interconnected variables, dependencies, and interactions. Symbolic artificial intelligence systems may struggle to handle the combinatorial explosion of possibilities and the intricate relationships between different components of the problem. As a result, they may lack scalability and efficiency when dealing with highly complex domains or large-scale problems. Predefined knowledge representations. Symbolic artificial intelligence systems rely on explicit knowledge representations and predefined rule sets, which may not capture the full complexity of real-world domains. Building and maintaining these knowledge representations can be labor-intensive and require domain experts to encode their expertise manually. Moreover, these representations may become outdated or insufficient to handle evolving problem domains or new scenarios. Lack of flexibility and adaptability. Symbolic artificial intelligence systems often lack the flexibility and adaptability needed to respond to changes in the environment or problem requirements dynamically. Modifying or extending the rules and knowledge base of a symbolic system can be challenging and may require significant effort, hindering its ability to adapt to new situations or learn from experience. Inability to learn from data. Symbolic artificial intelligence systems typically do not have the capability to learn directly from data, as they rely on predefined rules and knowledge representations. This limits their ability to leverage the wealth of information available in large datasets or to adapt their behavior based on observed patterns or feedback from the environment. Despite these limitations, symbolic artificial intelligence has made valuable contributions in various domains and continues to be used alongside other artificial intelligence approaches such as machine learning and probabilistic methods. Hybrid approaches that combine symbolic reasoning with statistical learning techniques aim to overcome some of these limitations and harness the strengths of both paradigms for more robust and versatile artificial intelligence systems. Despite its limitations, symbolic artificial intelligence played a foundational role in the development of artificial intelligence, and its influence continues to be felt in modern artificial intelligence approaches. Knowledge representation. The structured and explicit representation of knowledge developed in symbolic artificial intelligence remains relevant in modern artificial intelligence systems, even though machine learning models often learn representations directly from data. Incorporating symbolic knowledge representations can provide interpretability, reasoning capabilities, and domain-specific constraints. Logic and reasoning. Logical reasoning techniques developed in symbolic artificial intelligence, such as deduction, induction, and abduction, have been integrated with machine learning models to enhance their interpretability, robustness, and decision-making capabilities. Techniques like logical inference, constraint satisfaction, and theorem proving are used in hybrid artificial intelligence systems to combine symbolic reasoning with statistical learning, expert systems, and rule-based systems. While standalone expert systems and rule-based systems have limitations in handling uncertainty and complexity, their principles are integrated into modern artificial intelligence systems through rule-based inference engines, decision engines, and expert models. These components provide domain-specific expertise, business rules, and decision support capabilities in various applications. Natural language processing, symbolic artificial intelligence techniques for semantic analysis, syntax parsing, and understanding language structure have influenced modern natural language processing systems. Hybrid approaches combine symbolic linguistic knowledge with statistical models, neural networks, and deep learning architectures to achieve state-of-the-art performance in tasks like machine translation, sentiment analysis, and question answering. Cognitive architectures. Symbolic artificial intelligence inspired the development of cognitive architectures that aim to simulate human-like cognitive processes such as perception, memory, reasoning, and decision-making. These architectures, often based on symbolic representations and rule-based systems, are combined with machine learning techniques to create intelligent agents and autonomous systems capable of complex cognitive tasks. Explainable artificial intelligence. The emphasis on explicit knowledge, representation, and transparent reasoning in symbolic artificial intelligence has influenced the development of explainable artificial intelligence techniques. Explainable artificial intelligence methods aim to provide interpretable explanations for artificial intelligence models, decisions, and predictions, drawing on symbolic reasoning, rule-based systems, and causal models to enhance trust, accountability, and transparency. Overall, while symbolic artificial intelligence alone may have limitations in handling uncertainty and learning from data, its foundational concepts and techniques continue to be integrated with other artificial intelligence approaches such as machine learning, deep learning, and probabilistic reasoning. Hybrid artificial intelligence systems that combine symbolic reasoning with statistical learning aim to leverage the strengths of each approach to build more robust, interpretable, and adaptable artificial intelligence systems for a wide range of applications.